Alright, so I think I'm recording. Let's take a look at this problem. It's the same idea. We're looking at these rational functions, finding the x-intercept, the y-intercept, determining the end behavior, and identifying if there's any vertical asymptotes that may or may not exist, and if there's any holes that may or may not exist. To find the y-intercept, let's let x equal 0. That means basically principal substitution, substituting in. We often say plugging in 0 into the function. In the numerator, these first three terms will be 0, but then we've got a negative 12. Then in the denominator, the first two terms are 0, and we've got a positive 2. So my graph will intersect the y-axis at negative 6. What about x-intercepts? Let's see if there's any here. Oh, that says let x equal what? Let y equal 0. That's the output of the function. Remember, in function notation, the y values are f of x. So if a fraction reduces to 0, it's because of the numerator. And in the denominator here, x squared plus 3x plus 2. See, I have to be careful. Sometimes, if you ignore the denominator, it'll happen that there'll be a factor that's common to both the numerator and denominator. You won't recognize it, and you'll end up calling a whole an x-intercept, which is incorrect. So I can see that these four terms, that I can factor that by grouping. You could use your rational zero theorem if you wanted, but if I create a table and just enter in x cubed plus, I don't need the plus, 3x squared, I do need the negative, 4x and minus 12. Going across, these share a common factor of negative 4. Vertically, these share a common factor of 3. Horizontally here, an x squared. Vertically here, an x. So let's check. X squared times x is x cubed. X squared times 3 is 3x squared. Negative 4 times x is negative 4x. And at negative 4 times a positive 3 is negative 12. So my numerator definitely factors. And I can write that as x plus 3. X squared minus 4 factors to x plus 2 times x minus 2. Because x squared minus 4 is just a difference of squares. In the denominator, I've got x plus 2 times x plus 1. That's a plus. Alright, let's get rid of this table now. So before we set the numerator equal to 0, we recognize that there's some common factors that cancel here. X plus 2 divided by x plus 2. So I know there's going to be a hole in the graph. I don't want to just set this numerator equal to 0 and try to say that x equals negative 2 is an x-intercept, because I know it's going to be a hole. But I don't have any other factors that cancel, so this x plus 3 and the x minus 2, they yield an x-intercept of negative 3 and an x-intercept of positive 2. So I had a y-intercept of negative 6 and two x-intercepts, x equals negative 3 and x equals 2. Alright, so let's take a look at the end behavior. To determine the end behavior of a rational function, let's compare the degree of the numerator against the degree of the denominator, because for rational functions, the numerator and denominator are just polynomials. So in standard form, the degree is the largest exponent that the variable x sees here, which is 3, and here this is 2. I refer to this just as top-heavy because the degree of the numerator is bigger than the degree of the denominator. When it's top-heavy, there is no horizontal asymptote. So we want to answer, as x is approaching negative infinity, what are the y values doing? We know it's either going to be positive or negative infinity just from experience. in doing these problems. So the idea is what's happening far away from the origin, and up here in a negative sense. So if we plug in a negative value into this function, well, this x to the cube term, if you're extremely far away from the origin, it dominates. These other terms do not change that number hardly at all. If x is really, really small, heading towards negative infinity, these are insignificant. So I have a negative base raised to an odd power. In the denominator, the same idea. This leading term dominates, and the other values, as x approaches negative infinity, doesn't affect it really at all. So I have a negative number, but it's raised to an even power. So I have a ratio of a negative number divided by a positive number, because negative times negative is positive, and that ratio is negative. So I know that this y is approaching negative infinity. So let's figure out, as y approaches positive infinity, as x gets really big in a positive sense, what's happening to the y values? Well, again, it's this leading term here that dominates. So I've got some positive number that's being raised to an odd power, and again I've got some positive number that's being raised here to, I have a positive divided by a positive, and that ratio is positive. So I know y is heading to positive infinity. So here's my end behavior. Alright, now let's take a look and see if the graph has any vertical asymptotes or any holes in the graph. So we already said that we factored this, and I already forgot what I factored it to. So let me pause real quick. So earlier I had erased this tape. If you have these four terms, we could go in and do the rational zero theorem, but it's might be factored quicker to recognize if you put the first two terms horizontally, the last two terms in the next line, that you can factor both horizontally and vertically. X squared minus 4 is a difference of perfect squares that factors to x plus 2 and x minus 2. So we see that we do have factors that cancel. What does not cancel, I focus my attention in the denominator. I have one vertical asymptote. The domain, we excluded negative 2 and negative 1. The negative 2 we're going to see creates a hole in the graph, and the negative 1 is a vertical asymptote. I need to write it as an equation and not just say negative 1. It's actually the line x equals negative 1. So now, since these common factors here, I know that I have one hole in the graph. Holes, I need to provide the x and y coordinate, the location of the hole. Well, what canceled here was x plus 2. That set that equal to 0. X plus 2 equals 0. Well, x would have to be negative 2. If I plug negative 2 into the original expression, I'm going to get 0 divided by 0. I have to plug it into the reduced expression, which is x plus 3, x minus 2, over x plus 1. So let's do that down here, scratch work. If I have negative 2 plus 3, because instead of x plus 3, I'm using x is negative 2, and x is negative 2 minus 2, and then negative 2 plus 1. What is that? Well, in the numerator, negative 2 plus 3 is just 1, and 1 times, well, negative 2 minus 2 is negative 4, and negative 2 plus 1 is a negative 1. Negative divided by negative is positive, so I'm getting that negative 2 comma 4 is, the graph does not pass through that point. That's a hole in the graph. So I hope that helps for problem 6.